Good afternoon, everyone. Today, I'm really excited and happy to share with you some of the lessons which we've learned when we've been running code which is potentially malicious on our system. And by malicious, I mean code which is either designed intentionally or unintentionally to attack ourselves or other systems. So my name is Ben Hall. I've worked at various different companies at various different levels and roles, and I'm currently the founder of Ocelot Uproar, and we build products internally, as well as helping external companies with their development requirements. And today, what I really want to talk to you is what happens when you give an anonymous, unrestricted access to a Docker container and a Docker server and a daemon, and let the users just have complete control. And then how do we actually protect ourselves when we do this? All of these lessons are from a product which we're building called Scrapbook. Scrapbook is an online learning environment where we give environments pre-configured that users can use within the browser, for example, the latest version of Node.js with an editor. Alongside, we also have courses. So we've got a Docker course, and in order to run the Docker course, you need a Docker daemon. And we provide this in a browser that you can use without having to download or configure anything. And the lessons which we've taken can be applied in many different circumstances. So it's not just training, it's also multi-tenant systems. It's platform as a service. It's even continuous integration. It's where you're running code which is potentially untrusted, or you don't quite trust the third parties which have given it to you. And fundamentally, it's how you apply Docker security in practice. Now, before I begin, some of my examples would break your system if you run them locally. And so I would recommend that you don't run these locally or in production, because stuff will break and you will be put on the naughty list, and no one really wants to be there. So what happens when you give the users this environment? And so we've generally found there's two types of personalities in our users. The first one focuses on the course, they focus on the learning experience, and they have a great experience with the platform. The second type of user sees it as a challenge, and they see that they've got complete access, and they try and break it. And so they run through the basic commands. They look at which user it is and see who that is. They look at the current directories. They sniff around, poke around. Sometimes they install additional packages to find more information. And generally, they just get bored and try and delete everything. So this is all because the user is root. And this isn't a problem because Docker has built-in protection for us. And we can make the users more focused by changing the user which the container is running as. And this has an interesting approach, because once a user sees that they're running as root, they quickly just get bored and they quickly go back to learning and using the system as it's intended. But sometimes the user gets a little bit more interesting and they want to find more information out. So they start poking around and looking at uptime, they're looking at memory usage, how the disk layout and how much disk space is there and CPU. And this is all basic. It's just a little bit frustrating. Because Docker doesn't provide any kernel virtualization, you're actually talking to the host kernel. And as such, all of this information is leaking back through and leaking back to the container. But you can't really do much with it. You can just see how long my server's been running and when the last time I bothered to reboot it was. One information leakage which I'm a little bit more concerned about is in the host file. And this simply tells the container all of the other containers and their names and their IP addresses which are running on the host machine. And I personally have the mentality that if you can ping it, then the chances are someone is likely to hack it. And this is a potential problem and exposes and introduces more surface area for attack. And so you've got the inter-container communication flag, and so you can disable this. And while the files and the hosts are still listed, it does restrict your attack service. So once they find out more information, they generally try and reboot or shut down the container. Now, it's a container, so there's nothing to reboot. That is unless you're using net equals host when you launch the container. And when this happens, you change the namespace and give it additional privileges for the container. And as such, when you try and shut down the machine, or shut down the container in this case, it will actually shut down the host file. And so it's these types of features which we've had to be very careful not to introduce when we've been using and building on top of Docker for Scrapbook. So out of the box, Docker does provide us with an awful lot of functionality and an awful lot of protection. But as we've already heard today, it doesn't have the complete story, and there's certain things which are missing. And so that's what I'd like to go into a little bit more now, of what issues people are actually trying on top of Scrapbook. So the first one, let's talk about the CPU. So out of the box, we've got CPU shares. So when we start a container, we can give it a share of the CPU. This is great because it means that one container cannot saturate and run at 100%, locking out any of the processes or any of the containers running. But at the same time, it's only a share. It's only helping with priorities. If your container is running at 100%, it will stay running at 100%. Docker doesn't have anything to terminate or disconnect these processes. Now, generally, this isn't a problem. That is until you use this lovely special command called a fork bomb. And it looks a bit weird, but it's actually made up of very interesting things. So the first thing we do is we define a new function called colon. The body of this function calls itself, and then it pipes the response of itself into another function of itself. At this point, it disconnects and releases command, and after it's finished defining it, it calls itself. What happens quickly is that it calls once, this generates 2, this generates 4, and you get a nice big process tree running. And you can tell when someone has run this on your system because you'll have a CPU system load of 4,000% and 7,000 processes running. And before you hit about 8,000, your entire system crashes, and you need to do a hard reboot. This is a problem for us. And this is still a problem for us. Docker has got functionality in place, so you've got ulimits, which can restrict how many processes are running, but it's based on a particular user. And so in our system, we could actually be limiting real and actually valid behavior by introducing and using ulimits. And there's other new features coming in 1.8 and 1.9, for example, limiting the kernel memory. And while this goes a long way, it's still not a complete solution. And this is a problem. Another problem which we have are with log files. And this is probably the first attack which kind of got through and realized we needed to be a little bit more careful with how we built Scrapbook. And so I was prototyping, gave access to one of my friends, and my friend thought it would be funny just to echo hello world to the console. Turns out that my server can produce an awful lot of echoes in a tight loop very, very quickly. Alongside this, all of the responses were being stored in the Docker file and the Docker log file, which was being stored as JSON along with a timestamp. So it wasn't just the data which was being produced in the container, it actually grew a lot quicker because of the additional information in the log. And this wouldn't have been a problem, but I had kind of forgot to move the Docker directory to a different directory and a different partition. And so it quickly ate and used up 100% of the disk space on the only partition in the system. And then things started to break in very strange and weird ways. And it was embarrassing. So in 1.8, Docker now have log rotation. And so as long as you enable log rotation when you bring up the daemon, this shouldn't happen in future. And of course, you should always move the Docker directory to a different partition just so you don't chew up all of your OS hard drive space. But that's not the only problem. So you can also just allocate and create very big files. So when we first started, we tried to run fallocate, and it came back with operation not supported. And this made me very happy, because it saved me a lot of effort. If people can't allocate big files, then they can't fill up all the disk space. Turns out that this was only because I was running on ext3, and when we upgraded and changed servers to ext4, it had the functionality. And like with many things in software, just because this functionality wasn't supported, truncate and DDD definitely were. They may be a bit slower, but they can still generate a very big file very quickly. And without functionality for disk quotas built into Docker, users just had free reign, and they could do and create large files without very much restrictions. So, as I'm sure we're aware, there's one major directory. And so any changes which a user makes from the base image, is stored in the diff directory. So if you can manage the quota for that particular directory for the container, then you potentially had a way to restrict what the users could do and how much they could write. But it turns out that's not the only place information can be wrote to in Docker. Every container has the host file automatically mapped, which is stored in a different directory. So if you're running as root, and that means you can write to this file, and if you can write to it, you can fill it. And so not only do you have to manage the disk directory and how big that gets, you also have to manage the container directory, just in case someone figures out and tries to break it in different weird and wonderful ways. Alongside this, we've got networking issues. So out of the box, Docker is a great abstraction over IP tables. IP tables are something which I've still not really got my head around and really not configured them properly. So the fact that IP tables is configured by Docker on my behalf is great. I can restrict access from the outside, I can be confident that no ports are being opened without my knowledge, and I'm more confident of what is the surface area. That is until people kind of use reverse proxies, and they can run this on the container, and that will gain access to any port without any firewall restrictions. And it turns out that the bandwidth as a result is very difficult to restrict, not just in Docker, but also virtual machines and physical machines. Restricting bandwidth usage is difficult. It's not straightforward. And there are C groups, but that doesn't solve the problem. And you can shape the traffic using IP tables and TC, but this is confusing, this is problematic, and it's outside of the Docker runtime and ecosystem, and as such, it's something else you have to maintain and clean up after yourself. And the bandwidth is problematic in two ways. The first is inbound. Inbound generally indicates one of two things. Users are just intentionally wasting bandwidth for no good reason, or they're trying to seed the files for later use. Outbound is much more problematic for us. Outbound could be a potential DDoS attack being launched from the container. It could be them hosting a BitTorrent download, VPN, Tor relays, the list goes on. And this introduces us a lot of problems with our hoster, but also legal issues of what type of files are being hosted and potentially third from our servers. And this really makes it difficult to restrict, and it just feels sometimes like there's a big, massive leak. And so we've got these three core issues. We knew that Docker out of the box provided us with a lot of security, but if we couldn't resolve these three, then the product would have a lot of hard time, and people could break into it and hack it and destroy the system far too easily for our liking. So what did we do, and how did we resolve this problem? So we first started with using the Docker API and the Docker functionality. So out of the box, the docker diff command is really useful for seeing what's happened and seeing the changes on the system. You can be confident that any file touched, modified, or added gets listed without any additional noise. You've also got the bash history. So as users are typing in commands, you can see and watch what's actually happening. But as Mr. Robot has taught us, it's really not that hard to not make history and to not add your commands into the bash file. So we had to come up with new and more interesting ways to track people. And so we looked at Sysdig, which we've got an awesome presentation on later, and it's an amazing tool. Sysdig is extremely powerful, and it tells you an awful lot of information about what's going on. But sometimes it's too much information, and we also found it somewhat difficult to automate and take actions upon. So we built a separate service which logs the commands and what's happening on the actual box itself. But just logging isn't good enough. You need to be able to take action too. And so we built something called the Warden. The Warden watches and monitors. It sits on every single server within our cluster, and it watches for the malicious activity which I've been talking about. For example, the bandwidth, the CPU, and is there too much disk space being used? Because we're taking advantage of CPU shares, I can be confident that the Warden will always have access and always have priority in order to run the commands it needs to do, even if a container is spiking to 100%. Because it's on the box, we can talk over the Unix socket, so we don't have to worry about the bandwidth being saturated and the TCP problems and the network being down. the Warden can always monitor and always watch. And it's very similar to an intrusion detection system. It's just focused on Docker and the Docker containers being run. And there's lots more which I haven't covered. For example, privileged containers just open up a world of interesting opportunities for people, and being able to mount disks which have been mounted after the fact that the container has been launched and not through the Docker API. IP tables can open up some interesting opportunities and interesting side effects by using them if you don't turn off the flag. And the Docker socket is extremely powerful, and it gives you a lot of opportunities which is very difficult to restrict access to, especially if it's in a front-facing, especially if you've mounted it into a front-facing server, for example, Nginx proxy. If that gets hacked, they have access to your Docker socket file. That produces interesting results. And also, you just need to be careful of Docker images containing little presents. For example, I give you the promise and the dream of cute little kittens if you download and run my Docker image. But actually, if you want to run it, you have to run it by mounting a socket as well. Because I want to launch multiple containers, and I want to help you. Under the covers, actually what is happening is I'm simply just launching a privileged container. If I'm running a privileged container, I can pretty much do whatever I want to your host file, to your host server. I can mount directories, I can delete stuff, I can change the kernel. As I've already demonstrated, I could reboot. So I could change the kernel and then reboot your server, and then you would be none the wiser, just because I ran a privileged container. And so it makes it a very interesting challenge. But the Warden hopefully can protect most of these things. But what actually happens when it all goes horribly wrong? So, recently, before building Scrapbook, I wanted to play around with Elasticsearch. And so on the same virtual machine as what my blog is running on, I was like, I'll just spin up a quick container, just try a few different things, and then I'll delete it afterwards. Like, what's the harm? And as part of this process, I mounted a public-facing port into the container, and that's not a problem because I meant to turn it off, so nothing to go wrong. That is until you receive a nice little email from your hosting provider saying there's somewhat of a problem with your virtual machine, and we've disabled all the networking access. So I went into the control panel, looked at the bandwidth graph, and it was like, 560 megabits per second spike. That's problematic. That shouldn't have happened. And I went through a certain different stages. Denial is like, it must be the hosting provider. Like, that's ridiculous. The next one was, well, I don't even know how to generate that much traffic, so it definitely couldn't have been me. And then I realized it wasn't me, it was a hacker. So I did a little bit of sniffing around, looked at a host, and everything seemed to be normal. And then I investigated and looked, and it was a container. But this made me happy, because it's a container. And so by default, it was restricted, it was isolated. They couldn't have done too much damage, just because of the functionality out of the box from Docker. But obviously, they could launch a DDoS attack. And this got me thinking, what else did they do? So because Docker stores all of the standard out and the standard errors, I could see the errors which they were causing in Elasticsearch. And so I could see them running Java code, which they had uploaded, and this Java code downloaded additional files. It then executed. At one point, they did try and clean up after themselves, which I thought was extremely polite. But still, they didn't do a great job of it. And so, using Docker diff, I could see what files were being changed and what files they had modified. So as you can see in the top, netstat ps had been changed. I would imagine this is potentially trying to hide the fact that they're launching their own processes under the cover. They then proceeded to add a lot of temporary files. Some are security related, others are happily named DDoS 99, which I imagine that's what was causing all of the traffic in the first place. And so it was interesting. And so by using it and mounting it as a container, I could have a sniff around, I could see what they were doing, but I could be confident that a host file wasn't corrupt, it wasn't attacked in any different way. The container did its job and it restricted it. So this begs the question, is Docker secure in itself? And my viewpoint is yes, out of the box, Docker is secure. But it's only as secure as your best practices. And there are still weaknesses. And there are still gaps, and this is why people like Alex C and VMware are offering additional support and covering those bases which I've discussed. The hack, if that was hosted on the actual host machine, they would have had complete access. They could have changed any system files, and I would have been none the wiser. I would have deleted the directory, but they could have left things around like changing netstat or PS. I pointed out some of the bad things and some of the common things which people try when they first get access to us. But as we've been seeing a lot today, containers and deploying containers is a completely new game. With any new game, you have new rules, and you have new things which you need to abide by. For us, one of these rules was applying the Warden, and having the Warden watch what was happening on all of our systems. But hopefully that won't be needed in the future, and then the Warden can take a long and well-deserved holiday and look forward to his retirement. And with that, I'd like to thank you.